Hello everyone, welcome to this video on bias-variance trade-off. First, let's see what bias of an estimator means. In statistics, the bias of an estimator is defined as the difference between the expectation of the estimator and the true value of the parameter being estimated. That is, the expectation of theta hat minus theta. An estimator is considered unbiased if its bias equals 0. Otherwise, it is biased. Here is an example of estimating the mean and variance of a Gaussian distribution by the maximum likelihood principle. Let x1 to xn denote n examples which are sampled from a Gaussian distribution with unknown parameters mu and sigma. The maximum likelihood principle estimates these unknown parameters by maximizing the following likelihood function of training examples. We get that mu hat equals the sample mean and squared sigma hat equals the sample variance. We compute the bias of estimators mu hat and squared sigma hat and get that the bias of mu hat equals 0 and the bias of squared sigma hat equals squared sigma over n, which is not equal to 0. These results tell us that estimating the mean of a Gaussian distribution by the maximum likelihood principle is unbiased. However, estimating the variance of a Gaussian distribution is biased. High model complexity always means low bias of an estimator trained by the model. This is because the expectation of theta hat equals the best estimator trained by the model on enough training data. Since the concept set of a simple model is a subset of the concept set of a complex model, the complex model can always find an estimator with a smaller bias. The figure on the right side shows the relationship between bias and model complexity. Besides bias, another important concept is the variance of an estimator. In statistics, the variance of an estimator is the expectation of its square deviation to its expected value. Variance of an estimator is computed by the expectation of theta hat minus the expectation of theta hat all squared. High model complexity always means a high variance of an estimator trained by the model. The concept set of a simple model is a subset of the concept set of a complex model. Let theta hat denote an estimator trained by a model on a specific training data x1 to xn. x1 to xn are n instances sampled from p of x given theta. The squared error of theta hat can be decomposed as squared bias plus variance. I put the steps of verifying the above bias-variance decomposition equation for your studying here. The bias-variance trade-off equation tells us that the squared error of an estimator on testing data equals the sum of squared bias and variance. We have always known that increasing model complexity will decrease the bias of an estimator, but increasing the model complexity will also increase the variance of an estimator. The best model should thus have a medium value of model complexity. The dashed line on the right side shows the best model. It achieves the best bias and variance trade-off and has the smallest squared error on testing data. The gray line of the perfect model divides all models into 3 categories based on their model complexities. Underfitting happens if the complexity of a model falls into the left side of the perfect model. In this case, the model is not complex enough to fit training data, and the obtained estimator has high bias and low variance. The green line shows an example of the model which underfits training data. Overfitting happens if the complexity of a model falls into the right side of the perfect model in the bias-variance trade-off figure. In this case, the model is too complex and fits noise well, and the obtained estimator has low bias and high variance. The orange line shows an example of the model which overfits training data. Regularization is a commonly used approach in decreasing the variance of an estimator by decreasing model complexity. Many regularization methods have been proposed so far. For example, L1 norm regularization and L2 norm regularization. A linear regression model with L1 norm regularization is also called a lasso. A linear regression model with L2 norm regularization is called a ridge regression. First, let's see what L1 norm regularization is. Let theta denote all parameters in the model. L1 norm regularization is defined as the sum of the absolute value of each parameter. L1 norm regularization leads to sparse data and performs like feature selection. Let theta denote all parameters in the model. L2 norm regularization is defined as the sum of the square of each parameter. L2 norm regularization leads to small values of all theta and performs like weight decay. For both L1 norm and L2 norm, adding regularization will decrease model complexity and at the same time constrain bias of the model to a small value. Let H denote the concept set of the model without regularization, and HR denote the concept set of the model with regularization. We know that HR is a subset of H. Thus, the size of HR is much smaller than the size of H. Therefore, regularization decreases model complexity. Thank you for joining us.